Welcome to video 8, and the second one in our Quantum Finance series. We will have a look at Quantum Monte Carlo in pricing financial options. Every day, financial institutions price thousands of options. Some are straightforward, but for more complex ones, like path-dependent or exotic options, there's often no closed-form solution. That's where Monte Carlo methods come in. Powerful, flexible, but slow. A single option might need 1 million simulations just to converge on a fair price. Multiply that by thousands, and it becomes expensive. Before we dive deeper, let's quickly look at the kinds of options that financial institutions typically price, because these determine how complex the pricing challenge becomes. European option can only be exercised at maturity. American option can be exercised at any time up to and including maturity. Barrier option, activated or deactivated if the underlying hits a certain level. Asian option, payoff depends on the average price over a period. Look back option, payoff based on the maximum or minimum price during the option's life. Digital or binary option pays a fixed amount if a certain condition is met. Basket option. The underlying is a portfolio or basket of multiple assets. These aren't just academic categories, they define the pricing complexity and determine whether closed-form solutions exist. For many of these, there's no closed-form formula. That's why we need simulation methods like Monte Carlo, and why faster, smarter methods like Quantum Monte Carlo are so exciting. The challenge isn't just speed, it's accuracy, variance, and scalability. What if you need to price a barrier option in real time, or run a stress test across thousands of scenarios? Monte Carlo breaks down when time is tight and precision matters. Let's quickly recap how Monte Carlo pricing works for a European option. We define the option's payoff structure, simulate thousands of paths for the underlying asset, calculate the payoff for each, discount the results, and average them. That's it. Simple in theory, brutal in practice when scaled. Now imagine a quantum version. Instead of simulating one path at a time, a quantum computer builds a state that represents the entire probability distribution. From there, we can sample outcomes, ideally with fewer total queries. Here's a basic example. We price a 1-year European call option using 3 methods. Method 1. Classical Monte Carlo with 100,000 samples. The underlying's price development is simulated based on its volatility and a risk-free rate. We typically run this 1 million times or even more in real-world scenarios. Based on that, we get a distribution of the possible prices at the maturity date. This is not a normal distribution, but a log-normal distribution. This means it is asymmetric. The maximum of the occurrences, the mode is left of the average value. This happens because growth is multiplicative. For example, $100 minus 20%, then plus 20%, gives you only $96, less than the original $100. Then, we calculate the payoff of the option at maturity for the found underlying's prices. The average payoff is discounted by 1 year of risk-free rate to the present value. This is our option price. Method 2. Quantum Monte Carlo with a few thousand shots. For a European call option, we know that the underlying's terminal price follows a log-normal distribution under the Black-Scholes assumptions. That's what we encode into the quantum state here. Of course, for path-dependent options like barriers or Asians, we'd need to encode more complex distributions, possibly even simulate entire price paths quantum mechanically. As seen in video 6 on multi-qubit systems, the number of qubits span an option space with 2 to the power of the number of qubits possible states. Each quantum state acts like a bin, indexed by its binary value. Together they form a discrete grid over possible price outcomes. Now, we modify the amplitude for each quantum state in the way that we get to a discrete log normal distribution if we square the respective amplitudes. We use here only a slice of the total distribution in order to keep the accuracy high with the few qubits we have available in the simulator. We then measure the prepared qubits 1,000 times to extract the distribution along the desired log normal outcome. Just like in classical Monte Carlo, we still need many samples to achieve a stable estimate. Our error scales the same way, with 1 over the square root of the number of measurements. So while this quantum method might already be competitive in small cases, the real speedup comes later, when we introduce quantum amplitude estimation. Let's now look at the third method, the closed-form Black-Scholes formula, available only for simple European options. Method 3. Now for European options, we actually have a closed-form formula to calculate the price, the famous Black-Scholes formula. It's often used as a benchmark. But just to be clear, this formula only works for European-style options, not for American ones, or more exotic types like barriers or lookbacks. The work behind it was so impactful that in 1997, Myron Scholes and Robert Merton received the Nobel Prize in Economics. Fisher Black, who co-developed the model, had already passed away and couldn't be included. Alright, back to our comparison. Here you can see the results of all three methods, classical Monte Carlo, Quantum Monte Carlo, and the Black-Scholes formula. And at this scale, they all agree pretty well. So, no big quantum advantage just yet. You might be wondering, why don't the error bars always include the Black-Scholes value? Well, the error you see here is just the sampling error. Basically, the uncertainty that comes from a limited number of runs or measurements. But on the quantum side, we've got some extra limitations. For example, we're only encoding a central slice of the log normal distribution, so we're missing the tails. That's simply because we don't have enough qubits yet. With more qubits, we could capture the full distribution and get closer to the true value. So what's the point? Right now, Quantum Monte Carlo does not outperform classical Monte Carlo. And here's why. Current quantum computers are still far too small and error-prone to run meaningful financial simulations at scale. We're often limited to toy problems with a handful of qubits, and even then, noise distorts the results. But this isn't the end of the story, it's just the beginning. Research is advancing fast, and so is the hardware. The algorithms are already there. What's missing is the scale to unlock their full potential. The real promise comes from Quantum Amplitude Estimation, or QAE. In classical Monte Carlo, your error scales as 1 over the square root of the number of samples. But with QAE, we can theoretically achieve quadratic speedup. That means fewer samples for the same accuracy, pricing in seconds instead of minutes, or handling more complexity without exploding costs. Let's take a look at this plot. It shows estimation error versus the number of samples. Classical Monte Carlo is in red, quantum approaches in green and blue. Classical Monte Carlo shows a slow decay, 1 over the square root of n, while QAE variants fall much steeper at 1 over n. At our target error, classical Monte Carlo requires about 1 million samples, while quantum methods converge with just about 1,000 to 10,000 samples. That's the quadratic speedup in action. This is more than a math trick. Faster, more efficient pricing unlocks new capabilities. Better real-time hedging. Faster model calibration. Running large-scale simulations for risk, compliance, or regulatory stress testing. We're still early, but the roadmap is clear. Quantum Monte Carlo, powered by QAE, could reshape the entire derivatives pipeline once the hardware catches up. Alright, that's it for this session, our second video diving into real-life applications of quantum computing in finance. Thanks for sticking with me to the end. I'd love to hear your thoughts or questions, so feel free to leave a comment or send feedback. And don't forget to visit qubit-lab.ch, that's qubit-lab.ch, where you'll find all the videos in this series, along with Colab notebooks, Python code, and hands-on resources. Thanks again for watching. I hope you're starting to feel that unique quantum vibe. See you in the next video. Until then, take care and enjoy the quantum journey.